As part of my project of building an 8-bit homebrew out-of-order processor, I've been writing this assembler here. This allows me to take programs like this, which prints some message to the LCD and makes use of the instructions that my CPU has, and run them through the assembler to generate the binary representation that my CPU understands. By default, this just generates a binary dump, but I can run the assembler in verbose mode, which will reproduce the human-readable assembly. The main parts of the assembler that make this work are the parse instruction function, which reads the program written by a human and parses it into the internal representation of the assembler. Then there's a print instruction function, which allows the assembler to print the instructions back to the user in human-readable form for error reporting and to have this verbose output. And there's an encode instruction function that takes the internal representation and compiles it down into the binary format that the CPU understands. This all works pretty nicely, but there are 3 locations that I need to add new instructions to and make sure that I can parse the instructions, print them back out, and then encode them into their binary form. And if I zoom out here in this encode instruction function, you can see that this is just a whole bunch of repeated code that just slightly differs in the exact bits that get encoded into instruction stream. But most of this looks pretty similar and regular. And this is the same for the print instruction function and the parse instruction function. Today, I want to refactor the assembler a little bit and try to get rid of some of the repetition here. At the top of the assembler, we already have this list of opcodes, and ideally, I would want to have this list extended to not only contain the opcode, but also the encoding of the instruction and the kinds of operands they can have, such that we can have one encoding table for the instructions, and then the parsing, printing, and encoding would just use that lookup table of information to deal with the instructions. And then when we want to add new instructions, all we have to do is add them at the top of the file here. Ideally, when we're done with the refactoring, nothing about the behavior of the assembler changes. It should still produce the exact same output. And we already have quite a few assembler programs lying around. To get started, let's create a snapshot of the output that the assembler produces for each and one of these programs. Let me define a new rule that will just run the assembler in verbose mode and snapshot the output into a file. And then let's add a make target that builds these .out files. Basically, I'm going to grab a list of all the .s files in the directory, replace the .s with a .out, and then that's the dependency of this make target. This now allows me to type make all, which will go and build .out files for every .s file in the directory. And each of these .out files just contains the human-readable form of the program reproduced by the assembler, and then the binary encoding. Now let me take all these .out files and copy them to a new directory, and this directory will then basically be the ground truth, how we expect the assembler output to look like. And then as we make changes, we can compare against this and make sure that we don't break anything. Now that we have these reference files, let me tweak the makefile a little bit and add a check target that allows us to take the original file and the current version of what the assembler produces as an output, and then just diffs the two, which will then alert us to any changes we might have caused during the refactoring. And then we'll make the all target at the top just run all the checks for us. This now allows me to type make all to compare the outputs for all the programs. So let's go refactor the assembler a little bit. Let's first create a new data class which will describe the exact format and encoding of an instruction. And we don't want to have structural equality between these, so I'm just going to set eq to false. The instruction definitely needs a name, and we'll also want to store the individual instruction bits that we need to encode into the instruction stream. We've called these function 0 through function 3 in the decoder, and I think that's a pretty good naming scheme, so we'll just carry it over here. And then just after this class, I want to have this list of instruction definitions. And we'll start simple with just the NOP instruction, and that has all these instruction bits set to 0. When we parse instructions, it would be very handy to have a lookup table where we can look up an opcode format for a given instruction name. So let's create a dictionary for that. Then let me add a format field to the instruction class. This will basically allow us to create instruction objects and then reference the opcode format that those instructions follow. By default, we'll set this to none, but then as we move instructions over into this tabular form, we'll populate this font field and use that for all the different things we want to do with the instruction. Let's get started with instruction parsing, and let's see if we can parse this NOP instruction in the table here. Right now we do instruction parsing by checking whether we see a certain string at the current position of the input. But to make looking up instructions by name in this opcode table easier, let's just consume any sequence of letters and digits that look like an instruction into a string, and then we can use that string for the lookup. At this point, the name variable will contain this presumed instruction name, but that also means that all the instruction parsing we currently have is now broken, because that tries to parse the instruction name from the input instead of looking at this name field. And a quick check with the makefile shows you that the assembler now crashes on the very first instruction in the program. So let's change that over to use this new name variable. That looks a lot better. Most of the programs compile, but the directives, this .org directive here, for example, are still broken. And it's broken for the same reason. So let me move this directive handling, which is basically a special case, up ahead before the instruction parsing. And this now works again like a charm. Let's now take the instruction name that we've parsed, and let's try to look up an opcode format for this instruction. And in case we do find an opcode format in this table, we can just use that to construct an instruction object and return that. Let's see if this works by printing something to the terminal whenever we match one of these opcodes in the table. And yeah, the output is a little bit noisy, but you can see that for every NOP instruction in the input, we now match it using this table of opcode formats, and we use that to create the instruction object. And in fact, we can now go and delete the dedicated parsing for the NOP instruction. Let's do the same thing for the halt pseudo instruction, which also doesn't take any operands and should be fairly straightforward. The difference here is that the halt instruction has the function 0 bits set to the value 9. And even when I get rid of the dedicated parsing for halt, the assembler still works. Let's now use this opcode format information to print the halt and NOP instruction back in human readable form. This is going to be pretty simple because we don't support any operands or the like at the moment, so we'll just want to print the opcode of the instruction, which is stored in the name field of the opcode format. Most of the instructions will need a space after the opcode name, so we'll just include that right from the beginning. And then let's see if this works if I get rid of the explicit printing for the NOP and the halt instruction. Pretty cool, that still works. None of the diffs found any differences. And then as the final piece in the puzzle, let's also do that for the instruction encoding. This is going to be pretty straightforward since we don't support any operands at the moment. We just encode the func 0, 1, 2, and 3 fields directly. And if I get rid of the explicit encoding for NOP and halt, let's see if this still works. Pretty cool, looks like this is still working. All the diffs come out clean. Let's now try to expand this to also support instructions that have an RD register operand. A good example instruction might be this LCD command write or data write or command read data read, which just has a single RD register operand. Let's add these to the table. These instructions have a 4 in the function 1 field and the values 0, 1, 2, or 3 in the function 3 field. And where the function 2 field is, these instructions encode the RD register operand. To do so, I think I want to add an RD mode field to this opcode format class, which is going to be very similar to how the decoder deals with the various ways the RD operand might be used in an instruction. By default, we'll set this to unused. The assembler doesn't really need to know if we're reading or writing the RD operand. I think it just needs to know whether there's an RD operand or not. But I think in the future, when we try to generate this table of opcodes from like a single source of truth, the text file or this isa.txt file we've been writing up, this information will be present. And so might as well make the assembler work with it. When I rerun the assembler now, things are going to fail because the parser doesn't know how to deal with this RD mode we have in the opcode format. To fix this, we need to teach the parse instruction function how to deal with this RD mode. And by parsing a register and appending that to the operands list whenever the RD mode is not unused, this will make the assembler work again. Or more precisely, the parsing will now work, but now the encoding fails because we're trying to encode one of these LCD instructions, and the function2 field is not set for those instructions because the RD operand is in that place. So in here, after we've encoded the function0 and function1 bits, let's check the RD mode and encode the RD operand if it is used, or otherwise let's just encode the function2 bits. And this now allows us to encode these instructions with an RD operand. It looks like the encoding might work, but the printing of the instructions back to the user is not working. And that is true. Our print instruction function doesn't know how to deal with the RD operand. Let's go fix that too. And with this, we're able to print these LCD instructions back in human readable form. And since this is all working now, let me go and remove all the explicit parsing, printing, and encoding code for these LCD instructions. And this parsing code for the not instruction here is actually a good reminder that the LCD instructions aren't the only ones that have just the RD operand. Let me go and migrate all of the unary arithmetic operations that just have the RD operand over into this table format that we have. This small list here is now all that's needed to support these unary arithmetic ops. And indeed, the assembler is happy and still produces the same output, so I can go and remove all the bespoke parsing, printing, and encoding code for these instructions. As a next stepping stone, let's deal with instructions that can have an RS register operand. I'm going to define an RS mode, similar to how we have an RD mode, but this one is going to be quite a bit more complicated. Instructions can use the RS operand to encode just a single register read, but for absolute chumps and anything that deals with memory addresses, they can also interpret it as a 16-bit register pair. And then we have instructions that don't read from the register file to get the second operand here, but they interpret a few of the instruction bits as an immediate. And they do this in a few subtly different ways. The most basic one is to just take 8 bits from the instruction and using that as an immediate. But we also have instructions like the branches and the chumps that use an 8-bit immediate to encode a jump target. And this is a signed target because we want to be able to jump forward and backwards. And in the assembler, we need special treatment for these because we want to print a few more comments in the human readable format, but we also need to make sure that the jump offset is in range of a signed 8-bit number. And some instructions will interpret the bits in the RS operand field as a 4-bit signed immediate. Then let me add this RS mode to the Opcode format class. And then we can use this new field to encode a whole bunch of binary arithmetic operations. And now we need to go figure out how to deal with this RS mode field in the parser, the printer, and the encoder. Let's start with the parser. After we parse the optional RD operand, let's also parse the RS operand, which is either going to be a register, register pair, an immediate, or a jump offset. Then we also need to be able to print the RS operand back in human readable fashion. This is pretty straightforward. Again, we need a little bit of bookkeeping for the comma, and then we just want to have special handling for the jump immediates, because those we want to print as relative addresses, and we want to have a little bit of a comment at the end of the line. And instead of keeping track which exact operand index that the RD and RS operands are going to be in, I'm just going to create a list of operands that will just pop off elements as we print them. And finally, when we encode instructions, we also need to consider this RS operand. Now, one of the interesting things when we encode instructions here is that if the RS mode is set to an 8-bit operand, this will cover the function 1 field in addition to the function 3 field. So I think when we encode this operand here, we want to keep track of whether that happens or not, and then only afterwards encode the function 1 bits if they're not covered by the immediate. And with these changes, we can recompile all the programs, and all the binary arithmetic operations will be parsed, printed, and encoded with this instruction encoding table. It looks like there's a typo that needs fixing. And I can now go delete the bespoke parsing, printing, and encoding code for these binary arithmetic ops, and things will just continue working. This now also allows us to encode the load immediate and move instructions in this fashion. And the assembler still works. At this point, most of the remaining instructions have some kind of condition code associated with them. So we need to add a condition mode field to this opcode format that indicates how we're dealing with condition codes, and then we need support for that in the parsing, printing, and encoding. And there are two ways how we've been encoding condition codes. One way is to put them where the RD operand bits would be, and the other is to put them in the function 1 field. Then the first step is to teach the instruction parsing about the condition mode. And during instruction printing, we want to add the condition code to the instruction name separated with a period. And similarly for instruction encoding, we'll want to take the condition code and encode that either in the function 1 or function 2 bits. And with this final addition, I'm now able to recompile all the programs, and all the instructions in them are now encoded using this single table of instruction definitions and none of the bespoke parsing, printing, and encoding code that we had. And it looks like we're trying to encode function 2 bits when we're not expecting to. And yeah, this needs to check if the condition code covers the function 2 bits, and only if that's not the case do we need to encode the function 2 bits. So this means I can now go in and remove the final batch of parsing, printing, and encoding code. And even with all this bespoke code removed, the programs still assemble. Very nice. Let me refactor the parsing a little bit. Since all instructions now use this opcode definition table, we can just check if the instruction is contained there. Otherwise, we can error out and then continue. We don't need to have this if statement here and everything under an if statement. And we can do a similar thing for printing. And also for the encoding of instructions. Now, one of the interesting side effects of all of this refactoring is that we don't really use this opcode field on the instruction anymore. The only places where we need it is where we need to differentiate and have special treatment for compiler directives. But instead of using the opcode field for this, I think we can just create special opcode format objects for these directives instead. And with the directives moved over to a special opcode format object, the assembler still works. So this means we can get rid of this entire opcode enumeration here and also the opcode field on the instruction because it's no longer needed. Instead of having the opcode field, we can now make this format field mandatory in all instructions. And the assembler still works. At this point, we might as well rename this format field in the instruction to opcode again, and this opcode format class to just opcode. And that's all I wanted to do today. Instead of having bespoke parsing, printing, and encoding code all across this assembler, and every instruction has its bespoke little piece of code in 3 different locations, we now have this one list of opcodes which defines the instruction name, the binary bits that we need to encode in the instruction stream, but also how it interacts with the RD and RS operands and whether it has a condition code or not. And whenever we come up with new instructions in the isa.txt file, we can just add them here as well, and the assembler will have immediate support for them. And in case we have some fancier instructions that require slightly different parsing or printing, we can just add more of these mode fields to encode how these instructions would work. But everything follows a pretty robust pattern now, and we can just add new entries into this opcodes table here. And in the future, you can imagine that we could just take this isa.txt file that we've been writing, which contains the encoding details, and we can generate this list of opcodes here for the assembler automatically, and maybe even for the decoder. But that's going to happen in a future episode. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you next time.